All right, welcome to week 8, presentation 1, correlations and other relationships. The first couple slides here are stuff you've seen before in 701. And, well, to make a long story short, I'm going to provide you with this PowerPoint presentation. Most of it is the stuff I would say, so it actually has my notes embedded within it. You might also want to take a look at the lecture notes that I've provided, because there's some pages that have this material as well. So I'm just going to talk through the slides, since the slides actually have a lot of notes, just to sort of highlight a few items. Number one, correlation has this very long definition: causal, complementary, parallel, or reciprocal relationship, blah, 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 blah. It's basically, a correlation is, look at the bold letters, a relationship between two comparable entities. What kind of relationship? We don't know. It could be causal, it could be complementary, it could be parallel, it could be reciprocal. We don't know. We don't know until we do the analysis. So that's an important statement, as you'll find out as we move forward. So there's a little bit of danger in mistaking correlation with causation. They use some of the same visual elements. Mathematically, they share some mathematical elements. However, they're not exactly the same. Either mathematically, they are certainly not the same otherwise, because correlation is about relationships, of which causation is but one kind, so don't confuse the two. Now, this can be expressed numerically. This is detailed in the book, and, well, to make a long story short, I'm going to go on to the next slide. This is the statistics. Sorry, this is like the formula, which I'm actually going to break down and explain to you in a few slides. It's also explained in the book. It's also explained in other presentations. But basically, it has to do with the covariation of x and y relative within each other relative to the variation between each other. What does that mean? I'll explain in a few slides. You can illustrate as a picture. I'm going to talk about this in a few slides in a little more detail. Those lines are called the lines of best fit. By the way, if you want a reminder of how to do this, I covered this in a screencast in either week 1 or week 2, where I showed you how to do a scattergram. So I'm going to actually do another screencast this week that shows a few more tricks associated with this. And there's a relationship. That's nice. Okay. So the basic idea is that, as I said, it measures the strength of the linear relationship between two variables, two comparable variables. And in this case, they're either interval or ratio. There are kinds of correlation statistics called the Spearman test, where it could be for a non-interval or ratio variable, but I'm not going to require you to actually know how to do that. It's a little more complicated. All right. So basically, when you're doing hypothesis testing with Pearson's correlation, you're either stating that there is no relationship between the two variables, or there is some kind of relationship between the two variables. There's your null and your... Oh, okay, so we're just going to continue on. When you're doing your measurement, you have to address the direction of the relationship, positive or negative. Positive relationship has a positive sign, but you don't have to include it. So like as x increases, y increases, or as y decreases, x decreases. In other words, if they both go in the same direction. Now, there are two different sort of aspects of this that are measured. One is the shape of the relationship, as it says there. We look for linear, but sometimes we have nonlinear, like a parabola, a curve of some kind. And I'll talk about that in a few slides. The intensity of the relationship, how strong is it? Here's some examples. The one on the left is a positive relationship, as the one is actually, as both of these are positive. As the one the one on the left is positive. As temperature goes up, the relationship of beer sales goes up. As temperature increases, coffee sales go down. So there's a negative relationship. In other words, as one is going in one direction, the other is going in an opposite direction. Some of the properties are listed on here. I'm just going to skip past this because you can, as I mentioned earlier, you can print out this entire PowerPoint as a PowerPoint presentation. I'm going to skip this because I really want to get to some of the other stuff. There's a couple conditions you need to be aware of. Scatter plots are those XY graphs. Look, you're going to see X and Y all over the place, and even though in other presentations and in other media I say don't use don't use y when you mean x sub 2. However, most of the formulas are done in x and y, so I'm going to use that vernacular because you're going to see it all over the place. But just know that you should not think of it as x causing y. You should just think of it as the variable that goes on the x-axis versus the variable that goes on the y-axis. Now, that's different for when we get to regressions. Regressions, we're actually saying x causes y, but that's another conversation for another screencast. All right, here's an example of plotting something out. Remember this back in the day when you're in 6th grade and they'd give you two pairs of numbers and you'd plot them out. Okay, this really bothers me, but again, I'm just gonna have to get over it. It's x sub 1 on the lower and x sub 2 on the upper, but whatever. Again, and I'm done getting hung up on this. I'm using the terminology or the symbols that are used in the formula so that you can help you understand it. Here's an example of a linear relationship. There's a fairly strongly positive correlation going on here. In terms of Pearson's R, it's 0.89. It's a very strong relationship. Here's another one. This is a moderate relationship. You can see that as it starts to flatten out and spread out, it's neither strong nor weak. It's sort of in the middle. And here's a strong negative relationship. There's a fairly strong line going downward. However, this is all over the place. This is very weak. There's a slight negative. You can see there's a downward slope. If you were to draw a line of best fit. Now let me just make a comment on line of best fit. A line of best fit is basically a line that represents all of the dots that you see there. And I'm going to address this in a screencast that is sort of like a part 2 to the previous screencast. All right, let's take a look at the formula. The formula has a couple elements that are put together. One, we have the mean. This is the formal way of writing the mean out, but it's basically the sum of all the x's divided by n. We have variance. We have the standardized score, the z-score. Okay, those are the basic building blocks. Now, once you put all of them together, which I'm going to show you on another slide, they basically have a fairly intuitive meaning. It's the degree to which x and y vary together, meaning as x and y change in a together kind of way, divided by the degree to which they vary separately. So we mathematically are assessing the togetherness and the separateness to come up with a score, which is R. Okay. Now, if you want to do the formula in a variation of Excel, so you can mess around with Excel and do this the hard way, but I'm going to show you the easy way in the screencast. But it's basically the correlation of x and y is equal to the covariance of x and y divided by the square root of the variance of x times the variance of y. That's a lot of math, and I promise this wasn't a math class, it's a painting class. So I'm going to show you in the screencast how to push a few buttons to get that. Now, I've already done that before. I'm just going to do what I did last time, only going to add a few more things. Here's the actual formula. See, the thing in the lower left is the spread or variance or the variability of the variable x. Sometimes it's referred to as the sum of squares. As you can see, it's the sum of each x minus the mean squared, and then you add that, each of those up. Here is on the top part, we have the cross product of x and y, which is a very fancy way of saying the covariability of x and y. So as you can see, it's the sum of each x minus the mean times the sum of each y minus the mean, and you add all that stuff up. Again, you don't actually have to do the math. I'm trying to illustrate for you so you can understand the sort of thinking behind it. When we do regression is actually a lot of the same formula, only with a few other elements added in. Remember, you have to look at the statistical significance when you're doing your assessments, and there's a table in the book, and it shows you how in the chapter how to actually read the table so you can determine whether or not your score is statistically significant. It is possible to have a non-statistically significant outcome that nonetheless has a strong correlation. And that's only because of the way the numbers work out, the way the formulas work out, which you don't have to understand the formulas themselves per se. You don't have to memorize them. This isn't a memorization class on math, but you should just appreciate the underlying idea, which is what I just said. All right. This is meant to illustrate the degradation of the correlation, and I'm going to do this in a screencast, so stay tuned for that. These are just examples of, here's something where we did a scatter plot and we calculate the R of being negative 0.54. It's a moderate. As you can see, there's a line there. It's a line of best fit, and it's got a negative, it's going downward. This one is strongly upward, 0.85. Here's one is strongly downward, 0.94. As you can see, the higher the number up to 1, the tighter the dots get, meaning there's less variance. The closer and closer to 1, the less variance. At 1, there is no variance. Why? Because what we're saying is, whether up or down, that there's a 1-for-1 ratio. As x goes up by 1 value, so does y. Or as x goes down by 1 value, so does y. So this is just a few more, examples. Yay, examples. This R of 0.717, very weak. Look, they're all over the place. Is it going up? Is it going down? It's a little bit up, but almost nothing. Tight. Very tight. This is a perfect positive correlation, which very rarely happens, but it does every now and then. All right. Here's some examples of some of the issues that are specific to Pearson's correlation. Just to illustrate how an extreme data point can influence the value of the correlation, if you look at the lower left, there was a R of negative 0.05, very loose, very bad. Add one more data point, and look, all of a sudden it gets very strong. Now this is something you're gonna think. This is why I want you to learn how to check your data for outliers, because outliers can really skew. Sorry, it doesn't have to be skew your curve, but it can really impact whether or not you consider something to be good, bad, indifferent, or whatever. Degrees of freedom has to do with the number of for correlations has to do with the number of observations minus the number 2. And you have to look at the Pearson correlation table to identify the critical value. That's for statistical significance based on your degrees of freedom and your alpha. For our class, you should use 0.5. Now, here's an important statement. All the Pearson's correlation coefficient tells you is the general direction and how tight the data is. It does not tell you about percentage. Okay, for that we need something called R squared, which is called the coefficient of determination. It's a very fancy way of saying that we took our R value, we squared it, and that number yields a percentage that we can use. So for example, let's suppose you had a correlation coefficient of 0.4. If you square that, you'll find that it yields 16. In other words, we can say that 16% of the variance in the one is shared with the variance in the other, which is not very, very strong. But it gives us a meaning that we can understand. Here's some examples. As you can see, R is 0. So obviously the R2 will be 0 in the, because 0 times 0. Look at the second one, R squared. Sorry, R is 0.6. So if you take 0.6 and square it, it yields 0.36, and that is interpreted as 36% of the change in the one is explained by the change in the other. So IQ scores explain 36% of the college GPA. Whereas in the last one, annual salary and monthly salary, clearly there's going to be a very strong relationship as we can see there. Spearman is basically a different type of correlation, which I just want you to know the name of it is and that it is possible to do it. It's basically a way of testing the variance with ordinal variables. Ordinal variables, but you don't have to really know how to do it. It's a little tricky. Not all your relationships are linear. If you get these bends, a non-linear relationship, a curvy relationship, there's ways of correcting for this. You basically square your term, but we're not going to have to worry about that in this course. But it is something you have to be aware of, that there are ways of correcting when you get this sort of thing. Okay, this is a correlation output showing the correlation of several different variables. relative to each other. So like, for example, look in the upper left-hand corner, you can see the correlation of age to age is 100, which of course was 1, which makes sense because it's correlating onto itself. I don't know what those other variables are, but this is just an example of a matrix where you basically can showcase the correlation between many variables at once. I'm going to show you how to do this in Excel in a screencast. I'm going to skip partial correlation. Actually, I don't know why I even put this in here. In terms of reporting correlations, this is actually done really nicely in the Salkind text. But like, for example, let's suppose we did a correlation of the findings of education and annual income. And we found that we had an R of 65 with the degrees of freedom. That's actually from the. Hold on a second. Let me just go there. Okay. This is how you would put the reported. You put your R value, your degrees of freedom, which is basically your n minus 2. 2 is the number of variables, and the probability that you are accurate, which in this case is a p-value of 0.01. People understand when they look at this stuff what the sample size is when you're looking at correlations written out like this, because it's just add 2 to the degrees of freedom. Okay, a couple of review questions. I'm not going to talk about these. They're more or less answered in here. So I'm just going to skip. Although if you have a question, ask your professor. Skip. And the end is near, and it sure is. So I'm assuming. So go on to the screencasts and whatnot.